Welcome back to this free training series on FEMA P-154, Rapid Visual Screening of Buildings for Potential Seismic Hazard, brought to you by the Federal Emergency Management Agency's National Earthquake Technical Assistance Program. This module will go through concrete and masonry FEMA building types. You're watching the 7th of 9 training videos outlined here. Module 1 was an introduction to FEMA P-154. Module 2 went over earthquake hazard and seismic performance of buildings. Modules 3 and 4 went over the RVS process. Module 5 covered key building performance indicators. Module 6 and 7, where you are now, will go over FEMA building types. Module 8 will be a class exercise, and Module 9 will provide some concluding remarks.
All right, thank you, Gigi. So Module 7, we're going to be talking about concrete and masonry and defining the building types associated with each of these materials. So concrete buildings first, then we're going to look into precast, and then masonry buildings. And so concrete buildings being our first one, we're going to talk about our C1, C2, and C3 building types for concrete. So here's an illustration of a concrete moment frame building, which is our designated as C1 in one of our 17 FEMA building types. And so we can see a frame structure that's constructed out of concrete. Our exterior wall cladding system can be a very simple glass curtain wall, or it could be heavier precast concrete panels. We can also have some infill walls between the frame elements, which is our beams and columns, but we can't have too many to be classified as a C1 or concrete frame building. Here's a photograph of a two-story concrete frame building where the concrete frame elements, the beams and the columns, are clearly visible, and we have a glass or glazing curtain wall in between the columns and beams, acting as our exterior barrier or boundary. For building type C1 performance, if we have older construction for concrete moment frame buildings, and like we discussed in the previous modules, we've got ductile behavior, and then we also have non-ductile behavior. If you recall, ductility is the ability to undergo significant deformation without collapse. Well, for concrete C1 moment frame buildings, non-ductile concrete frames, which generally are roughly 1980s and older, can be considered non-ductile. They don't have as much steel in the columns. And so we don't get the benefit of that in terms of good ductility. So this slide here is going to be a series of building columns. The top side are going to be a building column that exhibits reinforcement, seismic reinforcement, to provide us with good ductile behavior. The bottom is going to be illustrating a column that does not have sufficient steel reinforcement in it to where its behavior is non-ductile. And so we're going to basically displace this column, each of them back and forth, cycle them back and forth as an earthquake would, to see what the relative performance is between them. So we have two columns that are plumb, straight, up and down. The next level, we're going to push the columns to the right, and the top column, which is our ductile column, starts to crack. We see some cracks. The bottom cracks even more, and we start to get some crushing at the base of the column. The next cycle, going back the other way, we get a little bit of crushing at the base of the column, and at the top, a little more cracking for the ductile column. The non-ductile column at the bottom, we start essentially blowing out the concrete within the confines of the reinforcement that's there for the column. And we can actually see the column shortening. So the building is coming down, if you want to think of it that way. We cycle it again, and our ductile concrete column at the top exhibits similar behavior. We've got cracking. We've got some crushing of material at the base and top of the structure, but it's hanging in there. And then our non-ductile column, we actually, since we're removing or blowing out that concrete between the confines of our steel reinforcement for the column, that's taking all of our compression loads or gravity forces. And so our column loses all bearing strength, and it's trying to support the building above it, and it just collapses. And that's what's illustrated in the non-ductile column below. And then the shaking is stopped, and what we have is we've got our ductile column returning to a plumb condition with some cracking in the column, but we don't have building collapse. And our non-ductile column is basically flattened and has completely collapsed, and our building has likely come down with it. So here's a good example of that. This is a photograph of a 6-story building that underwent the 1994 Northridge earthquake in Southern California. And it's a concrete moment frame building. It had a glass curtain wall infilled between the columns, which part of this changed the relative dynamics and response of the building to the earthquake. And so it developed shear cracking in the columns right where the windows were. And my understanding is this building was so severely cracked in the columns, again, they're supporting gravity loads in the rest of the structure, that the city of LA did not allow anybody to go in and collect their personal belongings or business materials and contents and then evacuate the building. They actually demolished the building in place with all contents inside because it was so hazardous. And again, this is exhibiting behavior of an older concrete moment frame building, our type C1, which can be very vulnerable. This is a video that we're going to walk through. It shows 2 building types. It shows performance for a concrete moment frame, C1, and it shows what a concrete C2 or shear wall building, how it behaves, and the drastic difference between the two. Now, this is, the video is of a 6-story concrete frame building built on top of one of the largest shake tables in the world over in Japan. And this is the E-Defense Lab. They're doing some great work over there. And what you'll see is this building that they constructed on top of their shake table was subjected to the 100% ground motion for the Kobe earthquake, which was a year after the Northridge earthquake in '94. And so the first clip I'll just describe is we're going to show overall building shaking from the table. And then we're going to have a focused view, a close-up view of one of the lower story columns to where we have a architectural panel. It looks like concrete, and it's an architectural panel that's infilled between the columns. And right above that would be where our classic window would be for that particular floor. And again, we're at the lower elevation of the first floor. And we're going to see how that panel, that concrete panel, that is architectural panel that's in between the columns, is one of our classic vertical irregularities that we capture in the P-154 procedure. And that is we have a short column effect. And so that's one of our vertical irregularities that we look for. So this is modeling that. The columns, by the way, are non-ductile. So they constructed it with steel such that they have a non-ductile concrete frame, older concrete buildings. The shear wall is the next clip we'll see after that, and it's reflective again of non-ductile shear wall reinforcement, but you're going to see a big difference in how it behaves relative to the columns. The shear wall, it has a classic X cracking if you look really close. Particularly up in the upper left-hand side, you'll see the cracks opening and closing and some of the concrete dust coming out. So let me play it, and you can see, again, overall shaking. Then we're going to see a lower column in the first floor behavior, and then we're going to see a shear wall, which is our representative of our C2 building type. So here's our first floor column. And you can see that the concrete between the reinforcing steel has kind of blown out. You can kind of see the building shortening or settling as a result of that. And here's our video of the concrete shear wall. Much, much better behavior, even though it's not reinforced for seismic design today. Performs much, much better. So building type C2, so concrete shear walls. So C1 is our moment frame, C2 is our concrete shear walls. Here shows an illustration of concrete shear wall building. Even though there's a lot of perforations in the walls for the windows, you can see that vertically aligning, there's these narrower piers that go all the way up the side of the building, form the side of the building. Those are our shear walls. And so we actually have a whole bunch of little bitty smaller shear walls the length of the building that's shown here. But they're still acting as shear walls. Here's a photograph of a concrete C2 or shear wall building. And you can see it's classic concrete. It's got perforations from the windows, the architect, but we've got these piers that extend all the way up from grade all the way up to the top between the windows. So our piers are acting as our shear walls. Here's another example for performance from concrete shear walls. Performance is very good in concrete shear wall buildings, even if they really haven't been designed for seismic attention. They seem to perform much better than if we have frame buildings. And so this is illustrative of a condition where we've got a coupled shear wall. If you remember back, one of our vertical irregularities we look for. We have a coupled shear wall condition. We got shear wall on either side of kind of a central core area where we've got windows, a bank of windows, and we're seeing a lot of cracks that are already filled up with epoxy injection. So the cracks weren't severe enough to cause the building to be demolished. They were very repairable. Put epoxy injection in there and they pretty much restored the original capacity of the building. C3 or concrete frame with URM infills. The key thing with a concrete frame with URM infill walls is this is a concrete moment frame, older vintage. So these represent old buildings, and oftentimes what they did was they had masonry that they infilled between the columns and the beams, and it's non-structural, but it acts in a structural manner in that it takes loads first, or seismic forces first, as our building starts to displace from the earthquake. And so what often happens is the masonry takes loads first, and if the shaking is stronger, cracking will occur, and then the load will redistribute to the actual concrete frames and joints. But C3, the key characteristic is old. These are representative old buildings. And so here's a real good example of a C3 concrete moment frame with URM masonry infill walls. You can clearly see the columns and the beams, and that are the color of concrete. And then you have the masonry infill, which is the color of brick, red, and infilled right between the columns and the beams. So very clearly evident this is a C3 building type. Like I said, performance is actually fairly good because we're taking the loads through the masonry. Wasn't designed for it, but it has capacity. And so it's resisting the loads within the wall systems. Once those crack, then the loads move or migrate to the frame, and then the frame takes the rest of the earthquake energy through its response. Part of concrete buildings are precast building types, so PC1 and PC2. PC1, I always like to think of PC1 as your big box warehouse. It's single story, it's concrete tilt-up walls, and then we've got a roof diaphragm, which can be wood, it can be metal steel joists with metal deck on top, but the big issue with these buildings is the connectivity or attachment of the roof diaphragm to the walls. That's kind of our critical vulnerability with these particular buildings. This is a photograph of the exterior of a PC1 building. Nothing exciting to write home about architecturally, just plain. They're representative of, you know, a lot of industrial type buildings. One of the issues, if you have a building with a timber or wood diaphragm, particularly an older one, there is a failure mechanism called cross-grain failure within the ledger. And the ledger is attached to the concrete wall. The wall is heavy, and so it tries to fall outwards, what we call out of plane failure for the wall. But its attachment to the diaphragm is such that the anchor bolt from the wall goes into the wood ledger, and then the ledger bends in a way that is timber is not designed for, to try to restrain the wall from out of plane response. Again, heavy, so therefore we have a lot of seismic out of plane load that has to be resisted back into the diaphragm. And these older buildings with this cross grain bending in the ledger just doesn't work, and the panel anchorage can fail, or the ledger fails, and then the panel falls out. There are some very straightforward retrofits for this type of condition. Here's a photograph of one such building, a concrete tilt-up with a timber roof, and there's proprietary retrofit or mitigation measures for this, where it's just a rod attached to the beams and purlins, and that's anchored into the wall panel, so we don't transfer load via cross-grain bending in our ledger, but directly into our roof joists and girder systems. Here's an example of a PC1 building where we actually had one side where the entire wall system collapsed, pulled away from the ledger, cross-grain bending. And we've got the right-hand side of the building where we had a partial roof failure, but the panels stayed vertical or erect. The panels actually didn't fall out. PC2, so precast concrete frame, is our next building type, FEMA building type. So this is like a concrete moment frame, but these are constructed of precast elements. So they're manufactured in the shop, and then they're trucked out, and then they're basically stood up or built up like a house of cards, if you will. And so the performance is related to the connectivity between all of those precast elements once they get out to the field and the building is under construction. And so here's an illustration showing kind of a different variety of some of these elements. There's what we call hollow core planks, which are literally our floor planks or roof planks. They've got literally long holes through them to reduce weight, and they're precast with reinforcing steel in them. Then we've got precast double T's, which is generally pretty common for parking garages. We can also have precast cladding for the exterior cladding system for these buildings, and then the beams and columns are all precast separately and trucked out to the building site. So here's a rather tall precast PC2 building, and if you look in very closely, you can actually see the star joints at the beam column interfaces or connections that were constructed. And then the next level is above that, along with the column. So design-wise, you really have to watch where the load is going and make sure it gets there because of all of these precast elements and the connectivity that you have to have between them for the building to perform very well. Where we see most of this type of building is in parking garages rather than office buildings, that is shown here. Here's an example of a PC2 building failure. And it's interesting to note in this photograph, you've got a 2-story parking garage. You have a shear wall, masonry shear wall that's shown that is intact, standing plumb, and the rest of the structure behind it is actually nearly collapsed. And so I always like this photograph because that's the lateral system for the building, is the shear wall. And so the seismic forces, inertia forces from the rest of the building elements needed to transfer to the shear wall to be resisted properly. And where we see is that connectivity was not achieved here during the earthquake, and the rest of the garage failed. The loads never got to the wall. The wall is still there standing perfectly. So nice undamaged shear wall. Let's switch to masonry. So we have three types within our masonry material type. We have RM1, RM2, and URM. And so here is an illustration for an RM1, reinforced masonry with flexible diaphragms. And so generally what you'll see in an RM1 is a one-story building, and you're going to have a timber or wood roof diaphragm system, or you're going to have steel joist with metal deck with insulation on top of that. And so that's what both of those are flexible diaphragms and typically associated with our single-story building. And so our walls are reinforced. Here's a photograph of an RM1 single-story reinforced masonry building. Again, they generally are industrial oriented, so nothing to write home architecturally about. But they're basically fairly regular. They're a box or a rectangle, and so we've a very regular lateral system for them. We can have masonry brick walls reinforced, and so we've got two widths of wall, which is two layers, if you will, with a gap between them. And in that gap, we have reinforcing steel that then is fully grouted. And so the overall wall system behaves as a grouted reinforced masonry shear wall. Not too common where we see brick formed as a shear wall like this. Where we see this more so is with concrete masonry units that are reinforced. And we can have concrete masonry units unreinforced, and we can also have concrete masonry units reinforced. So reinforced brick masonry wall. Here's a photograph of an opening within a brick reinforced masonry shear wall. And one of the telltale signs is that if you look in the opening at the edge, you'll see a vertical line that looks like concrete. Well, that's grout. And so it's a pretty good telltale sign that they've actually reinforced the cavity there between the two layers of brick, and we have a reinforced masonry shear wall system. Here's the more common type of reinforced masonry shear wall that we see type of building, and that is using concrete masonry units, or CMU, for an RM1. So there is a single story building. It shows some cracking at the very top. So this is after an earthquake, and the cracking probably occurred due to some torsional aspect in the building where the building was rotating, which is not evident in the photograph, but that's generally where you'll see that if a torsion is a component of the building response during earthquake shaking. RM2, our next building type, reinforced masonry with stiff diaphragms. Where you will see this is multi-story masonry buildings. And so they're going to have some level of concrete floor system forming a stiff diaphragm at each of the floor levels. And so that gets us into an RM2. Performance is a little bit different than an RM1. So the scoring is different associated with it. That's why there's a differentiation here. But here's a kind of a illustration of an RM2 building. So we've got our stiff floors, concrete floors. Those could be made out of hollow core planks with a topping slab on top, or poured in place concrete. And then the walls are masonry units, and the floors are tied into the walls or reinforced into them. And so our primary load path is from the floor diaphragm systems into the walls, acting as shear walls down to our foundation system. And so here's a good illustration or sketch of one of our floor systems that is bearing on our wall, perimeter wall system. And then there's a topping slab on top of those planks, precast planks, that's been poured, has reinforcement in it, that then goes into the wall system, and that gets all reinforced with grout. And so our elements are tied together very well, which is what we like. And so we have a good load path to transfer our seismic forces. And so here's a great photograph of a 3-story, looks like an apartment building, or it could be a good example for dorm rooms in a college. But you'll see we've got straight sections of nice reinforced masonry piers all the way up, and then we have our windows stacked on top of each other, and we have another pier. And so it behaves very much like a shear wall building is what it is, but it's masonry, and performance is generally very good as a shear wall system. Here's showing a photograph of our same building we just looked at, but it was shaken in an earthquake. And we've developed some X cracking between the windows at the first floor level, which is actually where we would exactly expect it, because that's our weakest cross section through there. Our forces are higher at the base of our structure. And so the building is behaving exactly like we would expect it to. Unreinforced masonry. This is one of our most vulnerable building types that we have of the 17. And it doesn't take much shaking to actually cause some pretty significant damage and life safety risk associated with these types of buildings. They are very pretty, but if you shake them, they are going to be damaged fairly quickly. And so here's an illustration of unreinforced masonry building, much like our reinforced, but no reinforcement. And so we've got typically a wood diaphragm system and floor and roof system for these buildings. The floor systems joists bear on the perimeter walls, generally in pockets that are built into the walls. Telltale sign, here's a photograph of the exterior of the unreinforced masonry wall. What you'll find is that the outer layer of wall, roughly every 7 or 8 courses, they'll turn the bricks short distance out, and then the length of the brick goes towards the interior of the wall or the building, and that engages another wider layer of brick, and that's how they can make a wider wall. Again, all reinforced, unreinforced, but it's tying those whites together when they turn these bricks. And the shorter end of the brick is clearly evident at the exterior to give you a pretty good telltale sign that, yeah, that's an unreinforced masonry building, and that's how we should score it in a P-154 evaluation. Here's another photograph, 2-story unreinforced masonry brick building. Again, very pretty, very beautiful. We have got a lot of these within the United States. Every small town has unreinforced masonry buildings in their downtown region, for sure. And so we've got a lot of this type of older building. Performance, like I mentioned, it's one of our most vulnerable building types. This is a photograph from Christchurch, New Zealand, during their 2011 earthquakes. And damage for unreinforced masonry starts at the top. We generally have cantilevered parapets at the top. That's where our displacements are the greatest from dynamic behavior for the building. And displacements are bad for unreinforced masonry. They don't like them because our beams are just set in pockets and they pull away from the wall as the wall tries to fall outward. And that's where we tend to see the failures. And so we've got some large sections of wall and parapet that are very heavy, that are falling from a height. And so they can be very damaging, as well as life safety issues for anybody running out of the building until the shaking is stopped. We can, like I mentioned previously, we can have concrete masonry units that are unreinforced. And so here's a example, a photograph of a unreinforced masonry, concrete masonry unit building. And you can see the damage is at the top, not at the bottom. Because of the lack of reinforcement within the walls, and the greater displacement at the top is where we begin to precipitate failure or collapse of the buildings for unreinforced masonry. So with those concrete and masonry building types, finishing up here for our FEMA 17 building types, let's take a quick quiz here. So which older building type has performed most poorly in past earthquakes? Is it light wood frame, multifamily, multi-story, our W1A building? Is it steel moment frame, our S1 building type? Is it tilt-up concrete, PC1? Or is it unreinforced masonry, our URM FEMA building type? So I want you to pause the screen, think about it a little bit, come back, and then see if you got the correct answer. All right, Gigi, which building do you think has the poorest performance in past earthquakes of these 4 building types?
I think the answer is unreinforced masonry, for sure.
It is. Something that's really nice to be able to utilize for the P-154 document is take a look at the basic scores that are there on each of the 5 forms. And so compare, you can compare all of them, but if you just look at the URM basic score for a low seismicity region, that you'll see that the score is quite high. I think it's above 3. So if you're shaking an unreinforced masonry building in a low seismicity environment, you have a pretty low risk of collapse. But then if you pull the next form, which is our moderate form, and look at what the basic score is, the basic score is 1.9, which means you're already under our life safety cutoff score of 2.0. And we haven't even put in our vertical and horizontal irregularity modifiers yet, which are all negative, which is going to make the score worse, which is representative of the building being much, much more vulnerable. So just by comparing, once you know your building type to the various seismicity regions, you can get a very good idea on which building types are more vulnerable than the others. And unreinforced masonry, it's classic. So any questions?
How vulnerable are URM buildings? You already elaborated a little bit on this. And so it seems that they're always doomed. What's the point of evaluating them if they're always going to fail?
Well, it's very good to understand which buildings you have within your community that are representative of this building type, because then you can begin to make some planning decisions around, how to manage those buildings and the issues related to them post-earthquake. If I know that in my community that, this, and this building are unreinforced masonry, I'm going, after a P-154 evaluation, I'm going to pretty much know that, hey, I'm going to expect some pretty bad damage, likely collapse of these building types. And that, I'm going to likely be dispatching, search and rescue to these areas after, moderate to higher level of earthquake. I can also utilize that information to encourage the building owner to do some level of retrofit. There are some reasonable prescriptive retrofits for these types of buildings because they are so vulnerable and they've been developed that one can do. Tie your parapets back, tie your joists into your wall systems. And so there are some very cost-effective things that can be done that will actually improve the performance significantly for these buildings. So doing a 154 evaluation provides you a lot of information to better manage this potential hazard after an earthquake. Anything else?
So if I have a building and I can't tell if it's a C1 or a PC2, what should I do?
Sometimes it can be difficult. PC2, generally what you're going to see is very clear evidence of joints between the columns and the beams. But sometimes that will get covered up architecturally, so then it becomes difficult to see versus a concrete frame building. If you are unsure, it's a concrete frame type building, so you're in the PC2, C1 type of range. You're sure it's not old, so it's not a C3 building, right, with infill. And so we'll see this in our next module, but you can actually score both of those buildings at the same time if you're unsure. You've narrowed it down to those 2 building types. it's very efficient to just run both scores and then take the lowest score in terms of representing the actual risk to that particular building.
All right, so in the next module, Sarah and Mike will take you through a class exercise. This concludes module 7, FEMA building types, concrete and masonry. See you in the next one.